Somewhere in the southern sky, buried inside one of the most violent galaxy clusters ever detected, there is a black hole so massive that it breaks our ability to rank anything against it. Its estimated mass is 100 billion times the mass of our Sun. Not million, not billion in the familiar sense. 100 billion. That number is so extreme that the black hole's event horizon alone could swallow our entire solar system and barely notice. Scientists call it Phoenix A, and if the estimates are correct, it sits at the theoretical ceiling of how large any black hole can ever become. But the terrifying part is not its size. It is what its existence reveals about how unstable our confidence becomes when black holes reach scales this absurd. If you enjoy journeys into the most extreme corners of the universe, do me a favour and consider tapping that like and subscribe button. It genuinely helps more than you might think, and it means we get to keep exploring together. Now, get yourself comfortable. Let's begin. You already know what a black hole is, or at least you think you do. You have heard the description 1,000 times. A region of space where gravity is so intense that nothing, not light, not radiation, not information of any kind, can escape once it crosses a boundary called the event horizon. You have seen the animations. The swirling disk of superheated gas, the dark circle at the centre, the warped light bending around an object so dense that the rules of ordinary physics surrender in its presence. You have absorbed the language. Singularity, accretion disk, spaghettification. These words have entered popular culture so completely that black holes feel almost familiar, almost safe, like a predator behind glass at a zoo. You can admire it, study it, even feel a little thrill of danger, but it cannot touch you. This familiarity is a trap, because the black holes most people picture when they hear the term are small. Cosmically speaking, they are trivial. A stellar mass black hole, the kind formed when a massive star collapses at the end of its life, might weigh 5 to 30 times the mass of our Sun. That sounds enormous by human standards. The Sun itself contains 99.8% of all the mass in our solar system. It outweighs Earth by a factor of 333,000. A black hole weighing 10 suns is a formidable object. If one appeared at the edge of our solar system, you would not notice it with your eyes, but its gravity would subtly tug on the orbits of distant comets. Now multiply that mass by 1,000,000. That is where things begin to leave the familiar territory of stellar remnants and enter a regime so extreme that even the language we use to describe it starts sounding inadequate. Supermassive black holes sit at the centres of galaxies. Not some galaxies, essentially all large galaxies. Every major galaxy astronomers have examined closely enough to check appears to harbour one of these gravitational monsters in its core. They range in mass from about 100,000 solar masses at the lightest end to billions, and possibly tens of billions, of solar masses at the heaviest. Our own galaxy, the Milky Way, hosts one. It is called Sagittarius A-star, and for decades it was the closest supermassive black hole astronomers could study in detail. Its mass has been measured with extraordinary precision, thanks to decades of patient work tracking the orbits of stars that swing around it like planets around a sun, except at tremendous speeds across distances of mere light hours from the event horizon. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize in Physics partly for this work. Their teams independently confirmed that Sagittarius A-star weighs approximately 4 million times the mass of our Sun. 4 million solar masses. Let that number settle for a moment. Take every planet in our solar system. Take every moon orbiting those planets. Take the asteroid belt, the Kuiper belt, every comet drifting through the frozen outer reaches. Add all of that together and you get roughly 1% of the Sun's mass. Now take the Sun and multiply it by 4 million. That is the object sitting 26,000 light years away from you right now, hidden behind thick curtains of dust and gas at the centre of the Milky Way. It is not the largest supermassive black hole. It is not even close to the largest. By the standards of what astronomers have found elsewhere in the universe, Sagittarius A-star is modest, almost small. This is where most people's intuition about black holes ends. They know that supermassive black holes exist. They know ours weighs a few million suns. They might have heard that some black holes are bigger, and they assume, reasonably enough, that finding the biggest one is like finding the tallest building or the deepest ocean trench. You measure them all. You compare. You crown a winner. Simple, clean, definitive. That assumption is about to collapse, because the moment you start climbing above Sagittarius A-star's weight class, the measurements become harder, the uncertainties grow wider, and the very concept of a single definitive champion starts to crack under the strain. To understand why, you first need to understand how astronomers weigh these things in the first place. You cannot put a black hole on a scale. You cannot shine a light through it and watch how much bends. You can only measure its influence on the things around it, and from that influence, calculate backward to figure out how much mass must be producing it. For Sagittarius A-star, this was done by tracking individual stars. Some of those stars complete full orbits in as little as 16 years. By watching them trace out their elliptical paths over decades, astronomers could apply the same Keplerian mechanics that govern planets around the Sun and derive the central mass with impressive accuracy. The margin of error is small, the result is solid, but Sagittarius A-star is special, it is close. 26,000 light-years is practically next door in cosmic terms, and the stars orbiting it are bright enough and near enough to the black hole that their motions can be resolved individually. No other supermassive black hole in the universe gives us this luxury. The next closest major supermassive black hole sits at the center of Andromeda, 2.5 million light-years away. The stars around it blur into a smear of light at that distance. You cannot track individual orbits. You have to rely on other methods. One of the most common techniques involves measuring the velocities of gas and stars in the central region of a galaxy. Gas swirling near a supermassive black hole moves fast. The closer it gets, the faster it orbits. By measuring the spread of velocities, the so-called velocity dispersion, astronomers can estimate how much mass must be concentrated at the center to produce those speeds. The method works. It has been tested and refined over decades. But it involves assumptions about the geometry of the gas, the orientation of the galaxy, and the distribution of mass in the central region. These assumptions introduce uncertainty. For nearby galaxies where the central region can be resolved in fine detail, the uncertainties are manageable. For distant galaxies where the core appears as a tiny smudge of light, the uncertainties grow. Another technique uses the relationship between a black hole's mass and properties of its host galaxy. Astronomers have discovered tight correlations between the mass of a central black hole and the velocity dispersion of stars throughout the galaxy's central bulge. Bigger black holes live in galaxies with faster moving central stars. This correlation, known as the M-sigma relation, allows astronomers to estimate black hole masses even when direct measurements of the central region are impossible. But the M-sigma relation is a statistical tool. It tells you what mass is likely given the galaxy's properties. It does not tell you the exact mass of a specific black hole with the same confidence as tracking individual stellar orbits. There are still other methods. Reverberation mapping uses the time delay between variations in a quasar's brightness and corresponding changes in the light from surrounding gas clouds to estimate the size of the region close to the black hole. From the size and the gas velocities, mass follows. Maser emission from water molecules orbiting some black holes can be tracked with extraordinary precision using radio telescopes, yielding excellent mass measurements for a handful of systems. Each method has strengths and weaknesses. Each works best in particular circumstances. And crucially, different methods applied to the same black hole can sometimes produce different answers. This is not a failure of science. It is the nature of measuring objects billions of light-years away, using indirect evidence filtered through layers of assumption and modelling. At moderate masses, the differences between methods are small enough that everyone agrees on the approximate answer. Sagittarius A-star weighs about 4 million solar masses. Nobody seriously disputes that. The black hole at the center of Messier 87 weighs somewhere around 6.5 billion solar masses. There is some spread in the measurements, with different studies producing estimates ranging from about 3 billion to over 7 billion, but the general neighborhood is well established. Messier 87 deserves a moment here, because it represents the next rung on the ladder we are climbing, and because it holds a unique place in the history of black hole science. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. That black hole was M87-star, the supermassive black hole at the center of the giant elliptical galaxy Messier 87, located roughly 55 million light-years from Earth in the Virgo cluster. The image was extraordinary, not because it was beautiful in the conventional sense, but because of what it represented. For the first time, humanity could see the dark silhouette of an event horizon set against the glowing ring of superheated plasma orbiting just outside it. The shadow's size, combined with the known distance to M87, allowed an independent measurement of the black hole's mass. The result, approximately 6.5 billion solar masses, was consistent with earlier estimates from stellar dynamics. The methods agreed. The picture made sense. 6.5 billion solar masses is a staggering number. Compare it to Sagittarius A-star at 4 million. M87-star is roughly 1,600 times more massive. If Sagittarius A-star is a house cat, M87-star is a full-grown bull elephant. The event horizon of M87-star spans roughly 38 billion kilometers in diameter. That is larger than the orbit of Pluto. If you place this black hole where our Sun is, its event horizon would extend past every planet in our solar system and keep going into the void beyond. Light itself, travelling at nearly 300,000 kilometers per second, would need the better part of 5 days to circle its circumference. And yet, M87-star is still not the largest. Not even close. This is the part of the story where the ladder starts to feel less like a ladder and more like a staircase disappearing into fog. Because above M87-star, in the range of 10 billion solar masses and beyond, things get strange. The measurements become less certain. The methods diverge. The objects are farther away, harder to resolve, embedded in environments so extreme that even the surrounding galaxy can be overwhelmed by the radiation pouring out of the central engine. Astronomers have a term for black holes that exceed 10 billion solar masses. They call them ultramassive. The word itself is a signal that ordinary language has started straining. Supermassive already sounds extreme. Ultramassive sounds like something a science fiction writer invented after running out of real adjectives. But the term exists because the objects it describes occupy a genuinely different regime. They are not just bigger versions of M87-star. They live in different environments, they grew through different mechanisms, and they push the limits of what theoretical models predict should be possible. The environments matter enormously. The most massive black holes tend to live at the centers of the most massive galaxies, which in turn tend to sit at the hearts of massive galaxy clusters. These are not quiet neighborhoods. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies, oceans of superheated gas reaching temperatures of tens of millions of degrees, and enormous reservoirs of dark matter binding everything together. Picture the environment. At the center of a massive cluster sits a single colossal galaxy, usually an elliptical galaxy far larger and far older than the Milky Way. This galaxy did not grow the way ours did, through the gradual accumulation of gas and the steady formation of spiral arms. It grew through violence. Over billions of years, smaller galaxies fell into the cluster's gravitational well, spiraled toward the center, and were consumed by the central galaxy. Each merger added stars, gas, and dark matter to the growing giant. Each collision funneled fresh material toward the core, where the central black hole waited. The mergers were not clean or quick. When two galaxies collide, Their stars almost never hit each other directly because the distances between stars are so vast compared to their sizes. But their gas clouds slam together and compress, triggering bursts of star formation. Their dark matter halos interpenetrate and gradually merge. And their central black holes, if both galaxies have one, sink slowly toward the center of the merged system through a process called dynamical friction, where gravitational interactions with surrounding stars drain their orbital energy and pull them inward. Eventually, the two black holes find each other, spiral together, and merge, releasing a burst of gravitational waves and creating a single, more massive black hole. This process of hierarchical merging, galaxy eating galaxy, black hole merging with black hole, repeated over billions of years, is what builds the most massive objects in the universe. The central galaxy in a massive cluster is the ultimate survivor of this cosmic tournament. It has consumed dozens, perhaps hundreds, of smaller galaxies over its lifetime. Its central black hole has grown through a combination of mergers with other black holes and steady accretion of gas from the cluster environment. The cluster itself acts as a funnel, channeling material from across hundreds of millions of light years toward the center, where gravity is strongest and where the central black hole feeds most efficiently. The hot gas that fills the space between cluster galaxies, the intracluster medium, plays a critical role. This gas, heated to tens of millions of degrees by the gravitational energy of infall, glows brightly in X-ray wavelengths. In the cores of some clusters, this gas cools, condenses, and flows inward toward the central galaxy, providing a continuous supply of fresh fuel for both star formation and black hole growth. These cooling flows can deliver thousands of solar masses of material per year to the central regions, an astonishing rate that dwarfs the gas supply available to isolated galaxies like the Milky Way. This is why the largest black holes live where they do. They are the ultimate beneficiaries of cosmic privilege. Born in the densest environments, fed by the richest supplies of gas and merger partners, they have had billions of years to grow, and the theoretical models suggest they can grow very large indeed. But the models also suggest there should be a limit. Black holes grow primarily by accreting matter, pulling gas and dust into a swirling disk that gradually spirals inward and crosses the event horizon. As material falls in, it heats up and radiates enormous energy. That radiation pushes outward against the infalling material, creating a kind of natural thermostat. The more intensely a black hole feeds, the more radiation it produces, and the harder it becomes for new material to fall in. This balance point is called the Eddington limit, and it sets a natural cap on how fast a black hole can grow through normal accretion. The Eddington limit is not a hard wall, it is a balance point. At the Eddington luminosity, the outward force from radiation pressure exactly equals the inward pull of gravity on the infalling gas. Below this luminosity, gas falls in freely. Above it, radiation begins to blow gas away, choking off the fuel supply. A black hole can in principle exceed the Eddington rate temporarily, feeding in a chaotic, super Eddington burst, where gas is funneled inward through channels that shield it from the radiation. But sustained super Eddington accretion is difficult to maintain. The radiation finds its way out eventually. The gas gets heated and dispersed. The feeding frenzy ends. At the Eddington limit, a black hole doubles its mass in roughly 50 million years. That sounds fast, but it imposes a strict speed limit on growth when compounded over cosmic time. Starting from a seed of, say, 1,000 solar masses shortly after the Big Bang, and growing continuously at the Eddington rate for the 13.8 billion years the universe has existed, you would end up with a black hole of roughly 50 to 100 billion solar masses. That is the theoretical ceiling, give or take. But the ceiling is softer than it sounds, because no real black hole grows continuously at the Eddington rate for the entire age of the universe. Real black holes have duty cycles. They feed intensely for a period, then exhaust their local fuel supply and go quiet for millions of years before a new merger or gas inflow reignites their accretion disk. The fraction of time a black hole spends actively feeding versus sitting dormant dramatically affects how massive it can become. A black hole that feeds for only 10% of cosmic history reaches a much lower final mass than one that feeds continuously. Seed mass matters too. A black hole that starts from a heavier seed, perhaps formed through the direct collapse of a massive gas cloud rather than from a single dying star, gets a head start that compounds over billions of years of growth. And mergers matter. Two black holes of 10 billion solar masses merging into one instantly creates a 20 billion solar mass object without any accretion required, bypassing the Eddington limit entirely for that mass jump. All of these factors, the duty cycle, the seed mass, the merger history, the availability of fuel, and the efficiency of feedback, combine to determine the maximum mass a black hole can realistically achieve. Different assumptions about these factors produce different theoretical ceilings, ranging from about 30 billion solar masses under conservative assumptions to 100 billion or more under optimistic ones. This ceiling matters because the candidates for largest black hole ever found bump right up against it. They sit in a range where every additional billion solar masses requires an explanation. How did this black hole get so heavy? Did it grow through normal accretion, or did something unusual happen? Did it form from an especially massive seed? Did it experience a period of super Eddington accretion, feeding faster than the standard limit would allow? Did it gain mass primarily through mergers with other black holes rather than through gas accretion? These questions are not academic. They determine how much you trust the mass estimates for the most extreme candidates. Because when a measurement tells you a black hole weighs 100 billion solar masses, you are claiming that this object sits at or beyond the theoretical maximum predicted by standard models. That is either a spectacular confirmation that nature can reach the limit, or a signal that the measurement might be overestimated, or a hint that our models of black hole growth are missing something important. Any of those possibilities is fascinating, but they are very different conclusions, and which one you believe depends on how confident you are in the number. And at 100 billion solar masses, you are not just claiming a record, you are claiming that this specific black hole managed to reach the ceiling despite all the factors that should have slowed its growth. The Eddington limit throttling its feeding rate, feedback from its own radiation, heating the surrounding gas and cutting off the fuel supply, and the decreasing merger rate as the universe ages and galaxies drift farther apart. A mass at the ceiling is not just large, it is suspiciously convenient, sitting precisely where the theory says growth should stall. Either the theory perfectly predicted where this object would land, or the measurement has been nudged toward a value that happens to coincide with a theoretical boundary. Neither possibility is dismissible, and the tension between them is real. And confidence, at these scales, is fragile. Consider the practical challenge. The most extreme black hole candidates are billions of light years away. Their host galaxies are often shrouded in dense intracluster gas or overwhelmed by the blinding glare of quasar emission. Resolving the central region well enough to apply the most reliable mass measurement techniques is often impossible. Astronomers are forced to rely on indirect proxies, scaling relations calibrated on less extreme objects, or theoretical models that attempt to reconstruct the black hole's growth history from the observable properties of its environment. Each of these approaches can produce a mass estimate. Each estimate carries uncertainties, and when you are working in the range of tens of billions of solar masses, even a modest fractional uncertainty translates into an error bar spanning billions of suns. A black hole estimated at 50 billion solar masses might actually be 30 billion or 70 billion. The central value is the best guess, but the best guess is not the same as a confirmed fact. This is the reality that lurks behind every headline claiming a new record. When a news article declares that scientists have found the largest black hole ever, what it usually means is that a team has published a mass estimate for an object that exceeds previous estimates for other objects. The estimate is real. The science behind it is serious. But the confidence level is not the same as the confidence we have in the mass of Sagittarius A-star, where decades of orbital tracking have nailed the number to within a few percent. At the ultramassive end of the scale, We are not working with a few percent uncertainty. We are sometimes working with factors of 2 or more. This does not mean the measurements are useless. Far from it. It means that the record books, at the very top, are written in pencil rather than ink. The rankings can shift when a new study applies a different method, uses updated calibrations, or reanalyzes existing data with improved models. A black hole that sits at the top of the list this year might be revised downward next year, not because anyone made a mistake, but because better data or better models refine the estimate. The public does not generally see this instability. What the public sees is a leaderboard, a list of names and numbers that looks as definitive as a table of Olympic medal counts. Ton 618, Phoenix A. Holm, 15 A-star. The names circulate through documentaries and YouTube videos and Reddit threads, each one presented as though its mass were a settled fact carved into the bedrock of astrophysics. But behind the leaderboard, the community of scientists who actually work on these measurements knows something the public rarely hears. They know the list is soft. They know that the top entries depend heavily on which method was used, which assumptions were made, and how the uncertainties were handled. They know that some entries carry more observational weight than others, and that the most extreme claims often rest on the least direct evidence. They know that the difference between the number 1 and number 2 spots might be smaller than the error bars on either measurement, making the ranking effectively meaningless in a strict statistical sense. None of this diminishes the science. Measuring black holes at cosmological distances is one of the most technically demanding achievements in modern astronomy. Every mass estimate at the ultramassive end represents thousands of hours of telescope time, sophisticated data analysis, and careful modelling. The scientists producing these estimates are among the best in the world, and they are fully aware of the limitations of their methods. The uncertainties are not hidden. They are published in the papers, discussed at conferences, and debated openly in the literature. But the public conversation often strips away the uncertainty and leaves only the number. And when the number is 100 billion solar masses, the reaction is awe, disbelief, and a rush to crown a champion. This is the context you need before we talk about Phoenix A. Because Phoenix A is not just a big black hole with a big number attached to it. It is an extreme candidate sitting at the very edge of what theoretical models say should be possible, measured through a method that is powerful but less directly observational than the techniques used for closer and better studied objects. Its story is not a simple tale of discovery and confirmation. It is a story of estimation, modelling, and the unsettling realization that at the farthest reaches of the mass scale, the ground beneath our confidence begins to shift. The black hole at the centre of the Phoenix cluster is not merely claimed to be the largest ever found. It is claimed to be so large that it challenges the limits of how black holes grow, and the distance between claimed and confirmed is where this story gets genuinely unsettling. But before we arrive at Phoenix A itself, there is one more thing you need to feel in your gut. Not just understand intellectually, you need to feel the scale. Because the numbers we have been discussing so far, 4 million solar masses for Sagittarius A-star, 6.5 billion for M87 star, these are already numbers that exceed human intuition. They are large enough to be impressive, but abstract enough to remain safely inside the realm of big number trivia. What comes next is not trivia. What comes next is a mass so extreme that the event horizon alone spans a region larger than parts of our solar system that took spacecraft decades to reach. What comes next is a black hole so heavy that it outweighs not just stars, not just star clusters, but entire small galaxies. What comes next forces a question that sounds simple but turns out to be anything but. What does largest even mean when the candidates are this extreme? That question is waiting for us in the Phoenix cluster. A galaxy cluster so massive, so luminous in X-rays, and so violently active that when astronomers first detected it in 2010 with the South Pole telescope, it immediately stood out as one of the most extreme environments in the observable universe. At its center sits a galaxy. Inside that galaxy sits something that may be the most massive black hole humanity has ever identified. And the reason it terrifies scientists is not just its size. It is the fact that its size depends on how much you are willing to trust an estimate that has never been confirmed by orbital mechanics, that was derived from modelling rather than direct spectroscopic observation of gas velocities, and that places this object at the absolute theoretical ceiling of black hole growth. If the estimate is right, Phoenix A is not just the record holder, it is a black hole pressing against the wall of what the universe permits. If the estimate is even slightly off, the entire ranking reshuffles, and a different black hole, measured through a different method with its own set of uncertainties, takes the throne instead. Either way, the story is not simple. And that is exactly what makes it terrifying. In 2010, a team of astronomers pointed the South Pole telescope at the southern sky and detected something extraordinary. The South Pole telescope is a 10-meter radio telescope sitting at the Amundsen Scott South Pole Station in Antarctica, one of the most inhospitable places on Earth, chosen precisely because the cold, dry atmosphere above the pole is nearly transparent to the millimeter wavelength radiation the telescope was designed to detect. Its primary mission was to survey the sky for galaxy clusters using a phenomenon called the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background radiation caused by hot gas inside massive clusters scattering ancient photons to slightly higher energies. The effect is faint. Detecting it requires exquisite sensitivity. But when a cluster is massive enough and hot enough, the signal becomes unmistakable. The signal from the Phoenix cluster was unmistakable. Located in the constellation Phoenix, roughly 5.7 billion light-years from Earth, this cluster immediately stood out in the survey data. Williamson and colleagues reported the initial detection, and follow-up observations across multiple wavelengths quickly revealed why the signal had been so striking. The Phoenix cluster is one of the most massive galaxy clusters ever discovered, weighing in at approximately 2 quadrillion solar masses. That is 2 times 10 to the 15th power. Suns a number so large that writing it out in full would require 16 digits. To put that in perspective, the Milky Way, including its dark matter halo, weighs roughly 1.5 trillion solar masses. The Phoenix cluster outweighs our entire galaxy by a factor of more than 1,000. It is a gravitational colossus, one of the heaviest bound structures the universe has ever assembled. But mass alone was not what made the Phoenix cluster remarkable. It is also the most luminous X-ray cluster ever detected, pouring out more X-ray radiation than any other known cluster in the observable universe. The hot gas filling the space between its galaxies, called the intra-cluster medium, reaches temperatures of tens of millions of degrees, superheated by the gravitational energy released as matter falls into the cluster's enormous gravitational well. This gas does not just sit there passively, it glows furiously in X-ray wavelengths, radiating energy at a rate that eclipses every other galaxy cluster astronomers have measured. X-ray observations from the Chandra Space Observatory revealed the structure of this superheated gas in stunning detail. The gas fills the cluster like a luminous fog, densest at the center and thinning gradually toward the outskirts. Near the core, where the density and temperature peak, the gas is doing something unusual. It is cooling, not gently, not gradually, but at one of the highest cooling rates ever recorded in any galaxy cluster. Approximately 3,000 to 4,000 solar masses of material per year are condensing out of the hot phase and becoming available for other processes. In most galaxy clusters, the cooling rate is far lower because the central black hole acts as a thermostat, reheating the gas before it can cool significantly. In the Phoenix cluster, that thermostat appears to be overwhelmed. To understand why this matters, you need to understand how that thermostat is supposed to work, because its failure is the key to the entire Phoenix A story. The best studied example of successful feedback is the Perseus cluster, one of the brightest X-ray clusters in the sky, and one of the most thoroughly observed objects in extragalactic astronomy. At the center of the Perseus cluster sits the giant elliptical galaxy NGC 1275, which harbors a supermassive black hole, actively accreting material and launching powerful jets of relativistic plasma. Those jets do not simply shoot outward and dissipate. They slam into the dense intracluster gas surrounding the galaxy and inflate enormous bubbles, cavities of low-density plasma that push the hot gas aside and deposit their energy into the surrounding medium. Chandra X-ray images of the Perseus cluster reveal these cavities in stunning detail, dark voids surrounded by bright rims of compressed gas, each one tens of thousands of light-years across. They look like blisters in the X-ray fog, ghostly imprints of the black hole's power pressed into the fabric of the cluster's atmosphere. The energy budget in Perseus is roughly balanced. The amount of energy the jets deposit into the surrounding gas approximately matches the rate at which that gas would otherwise radiate away its heat and cool. The black hole heats the gas. The gas stays hot. It cannot collapse. Star formation remains suppressed. The central galaxy stays red and dead, dominated by old stars, with very little new stellar birth. This feedback cycle has been maintaining equilibrium in Perseus for hundreds of millions of years, perhaps billions. It is one of the most important regulatory mechanisms in galaxy cluster evolution, and it was long assumed to be universal. Every massive cluster, the thinking went, should have a central black hole powerful enough to prevent its gas from cooling catastrophically. The Phoenix cluster proved that assumption wrong. Phoenix A's central black hole is not absent. Radio observations confirmed the presence of relativistic jets, and X-ray images revealed cavities in the intracluster gas, just as in Perseus. The machinery of feedback exists. But in the Phoenix cluster, the machinery is losing. The cooling flow is so intense, so torrential in its rate of energy loss, that the jets cannot compensate. The energy being deposited by the black hole's feedback is vastly insufficient to offset the energy being radiated away by the cooling gas. The thermostat is running, but the building is losing heat faster than the furnace can produce it. The consequences of this failure are visible across the entire central galaxy. Because the gas is cooling faster than feedback can prevent, enormous quantities of cold, dense material are raining down onto Phoenix A, collapsing under gravity and igniting into new stars at a ferocious rate. The central galaxy was forming new stars at approximately 740 solar masses per year. For comparison, the Milky Way forms new stars at a rate of about 1 to 2 solar masses per year. Phoenix A was manufacturing new stars roughly 500 times faster than our entire galaxy. This is one of the most extreme starburst rates ever measured in the center of a galaxy cluster, and it stands in stark contrast to the quiet, red central galaxies that dominate nearly every other massive cluster astronomers have studied. The multi-wavelength study by M. McDonald and colleagues quantified the cooling flow in extraordinary detail. Their measurements showed a runaway cooling rate of roughly 3,820 solar masses per year, among the highest ever observed in any cluster core. The team noted that the feedback mechanism expected to prevent such runaway cooling, the heating produced by the central black hole, appeared to be inadequate to balance the radiative losses. In their framing, the Phoenix cluster was a system where the feedback loop had not yet fully established itself, or had been catastrophically overwhelmed by the sheer intensity of the cooling flow. The implications cascaded outward. If the cooling rate is this extreme, and if the central black hole has been feeding on this infalling material for a significant fraction of the cluster's history, then the black hole itself should have grown to an extraordinary mass. The gas does not just form stars. Some of it inevitably spirals inward toward the center of the galaxy and feeds the black hole directly, adding to its mass over billions of years. Some estimates suggest Phoenix A's black hole accretes roughly 60 solar masses per year, a rate that, sustained over cosmic time, would build an object of staggering proportions. This was the reasoning that led a team of researchers to attempt something ambitious. Rather than measuring the mass of Phoenix A's central black hole through direct observation of stellar orbits or gas velocities, which is extraordinarily difficult for an object 5.7 billion light-years away, they built a theoretical model of the black hole's growth based on the observable properties of its environment. The work was led by M. Brokamp and colleagues, who developed a method using the stellar density profile of the central galaxy combined with models of adiabatic black hole growth. The approach works like this. You begin with detailed observations of how the stars in the central galaxy are distributed, how their density changes as you move from the outskirts toward the core. This density profile encodes information about the gravitational potential at the center, which in turn is influenced by the mass of the central black hole. A more massive black hole alters the orbits of stars in the central region, puffing up the core density profile in predictable ways. By measuring this profile and comparing it to theoretical predictions for different black hole masses, you can estimate how massive the central object must be. But the model goes further. It incorporates the feedback relationship between the black hole's energy output and the behavior of the intracluster gas. The team deduced an energy conversion parameter that relates the black hole's accretion rate to the AGN feedback power, the heating efficiency that determines how much of the black hole's energy output couples to the surrounding gas. They then modeled how the central black hole may have grown over time by accreting material from the cooling flow, tracking the interplay between accretion, feedback, and the evolving properties of the cluster gas. By adjusting the parameters of this model until they match the observed properties of the galaxy and the cluster, including the stellar density, the gas cooling rate, the X-ray luminosity, and the radio-emitting cavities carved by the jets, they arrived at an estimate for the black hole's current mass. The result was staggering. The models indicated a central black hole with a mass on the order of 100 billion solar masses, possibly even exceeding that value, though the authors noted that the black hole's mass had not been measured through orbital mechanics. 100 billion, not million, not the mere billions of M87 star, or the tens of billions attributed to objects like TON 618. 100 billion times the mass of our Sun. To feel the weight of that number, you need to step away from abstraction and try to anchor it in something physical. Start with the event horizon. For a non-rotating black hole, the size of the event horizon is determined directly by its mass, through a quantity called the Schwarzschild radius. Double the mass, double the Schwarzschild radius. For a black hole of 100 billion solar masses, the Schwarzschild radius works out to approximately 295 billion kilometers. The diameter of the event horizon is therefore roughly 590 billion kilometers. In more familiar units, that is roughly 4,000 astronomical units from one side to the other. 1 astronomical unit is the distance from the Earth to the Sun. So the event horizon of Phoenix A's black hole, if the mass estimate is correct, stretches across a region 4,000 times the distance between the Earth and the Sun. Let that image build in your mind. Picture our solar system. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and distant Pluto, orbiting at roughly 40 astronomical units from the Sun. The event horizon of this black hole is 50 times the orbit of Pluto. It reaches outward to roughly the inner edge of the Oort cloud, that vast shell of icy bodies that marks the gravitational boundary of our solar system. If you place this black hole where our Sun is, its event horizon would swallow every planet, every moon, every asteroid, every comet in the inner solar system, and keep expanding outward past the Kuiper belt, past the scattered disk, past the heliopause where the solar wind yields to interstellar space, and come to rest in a region so remote that no spacecraft humanity has ever launched has come close to reaching it. Voyager 1, the most distant human-made object, launched in 1977 and now roughly 160 astronomical units from the Sun, after nearly 5 decades of continuous travel, would still be deep inside the event horizon of this black hole. It would need to travel more than 10 times farther just to reach the edge. Every milestone of human space exploration, every record-breaking distance achieved across nearly half a century of interplanetary flight, would be swallowed whole and still leave the overwhelming majority of this event horizon unfilled. Now, consider the circumference. A circle with a diameter of 590 billion kilometers has a circumference of approximately 1.85 trillion kilometers. Light travels at roughly 300,000 kilometers per second, which translates to about 26 billion kilometers per day. Dividing the circumference by that daily light travel distance gives you approximately 71 days. Light, the fastest thing in the universe, would need more than 2 months to travel around the event horizon of this black hole. Not across it, not through the interior, just around the edge. A photon, starting its journey around the equator of this event horizon in early January, would not complete the circuit until mid-March. The mass itself is difficult to put into meaningful perspective because no familiar object comes close. 100 billion solar masses is roughly 24,000 times the mass of Sagittarius A-star, the black hole at the center of our own galaxy. It is roughly 15 times the mass of M87 star. It exceeds the total stellar mass of many entire galaxies. The Milky Way, with its estimated 400 billion stars, contains a total stellar mass of roughly 50 to 64 billion solar masses. Phoenix A's black hole, if the estimate holds, outweighs all the stars in our galaxy combined. By a comfortable margin, every star you have ever seen in the night sky, every sun around which every known exoplanet orbits, every stellar nursery and red giant and white dwarf in the entire Milky Way, all of them added together, still fall short of the mass concentrated inside this single object's event horizon. This comparison is worth pausing on because it crosses a psychological boundary. We are accustomed to thinking of black holes as objects that live inside galaxies, embedded within a much larger structure of stars and gas and dark matter. A black hole might dominate the central region of its galaxy, but the galaxy as a whole is incomparably more massive. Sagittarius A-star weighs 4 million solar masses. The Milky Way weighs roughly 1.5 trillion solar masses when you include dark matter. The black hole is a speck compared to its host, but at the ultramassive end of the scale, this relationship begins to distort. A black hole of 100 billion solar masses sitting inside a galaxy, even a galaxy as enormous as Phoenix A, represents a far larger fraction of the total system's mass than anything we see in normal galaxies. The black hole is no longer a small engine buried deep in the core. It is a gravitational anchor so massive that it begins to rival the stellar mass of the galaxy itself. The tail does not wag the dog, but it is getting close. Now here is where the crucial caveat enters the story, and where intellectual honesty demands that we slow down and be precise about what we know versus what we estimate. The 100 billion solar mass figure for Phoenix A is not a direct measurement. It was not obtained by tracking the orbits of individual stars around the black hole, the way Sagittarius A-star's mass was determined. It was not derived from resolved spectroscopic measurements of gas velocities in the immediate vicinity of the event horizon. At 5.7 billion light-years, the central region of Phoenix A is far too distant for current telescopes to resolve the sphere of influence where the black hole's gravity dominates over the galaxy's stellar mass. The angular size of that region on the sky is far too small to isolate with even the sharpest instruments available today. Instead, the estimate comes from modelling. Sophisticated, physically motivated modelling grounded in real observations of the galaxy's stellar density profile, the cluster's gas properties, and the feedback signatures visible in X-ray and radio wavelengths. But modelling nonetheless. The method starts with a theoretical framework, feeds in observed parameters, and produces a mass that is consistent with the observations under the assumptions of the model. If the assumptions are correct, the mass is likely in the right ballpark. If some of the assumptions are off, if the stellar density profile is influenced by processes the model does not fully account for, or if the feedback efficiency differs from what was assumed, the mass could be significantly different. This does not mean the estimate is unreliable. The modelling approach used by Brockamp and colleagues is well established in the study of black hole growth in galaxy clusters. It has been applied to other systems and has produced results broadly consistent with more direct measurements where those are available. The fact that Phoenix A's extreme cooling flow, extraordinary starburst rate, and energetic feedback signatures all point toward an exceptionally massive central engine lends additional support to the estimate. The number did not appear from nowhere. It emerged from a convergence of independent lines of evidence, suggesting that something extraordinary is happening at the center of this cluster. But convergence of indirect evidence is not the same as direct measurement. The difference matters, especially when the number in question pushes against the theoretical limits of black hole growth. When a mass estimate places a black hole at 100 billion solar masses, it is claiming that this object sits at or near the absolute ceiling of what standard astrophysical models predict. That is either a remarkable discovery, confirming that nature can push all the way to the limit, or a signal that the estimate might be too high, inflated by modelling assumptions that do not perfectly capture the real physics of this specific system. It is worth noting that not all assessments agree on the magnitude of this estimate. While the Brokamp modelling work points to approximately 100 billion solar masses, at least one independent assessment has suggested a range closer to 10 to 20 billion solar masses for the central black hole, based on different assumptions about the accretion history and the relationship between the black hole and its host galaxy. The discrepancy is enormous, spanning nearly an order of magnitude, and it underscores just how model-dependent the result is. 10 to 20 billion solar masses would still make Phoenix A's black hole extraordinarily massive, firmly in the ultramassive category and among the heaviest known. But it would be a fundamentally different object from one weighing 100 billion. The gap between these estimates is itself larger than the total mass of M87 star. It is a gap wide enough to contain several of the most massive black holes ever measured and still have room left over. This range of estimates is not a contradiction. It is a consequence of different groups applying different methods with different assumptions to an object that is extraordinarily difficult to characterize at such a vast distance. The groups are not disagreeing about the observations themselves. The X-ray luminosity, the cooling rate, the starburst activity, the jet cavities, all of these are measured quantities that everyone broadly agrees on. The disagreement lies in how those observations are translated into a mass for the central black hole. Different models emphasize different aspects of the data. Different calibrations produce different outputs. And at the ultramassive end of the scale, small differences in methodology can propagate into enormous differences in the final number. Both possibilities are scientifically interesting. Neither is dismissible. And the tension between them is exactly what makes Phoenix A such a fascinating and unsettling object. Consider what happens if the high estimate is accurate. A black hole of 100 billion solar masses would confirm that nature can produce objects at the extreme end of theoretical predictions. It would validate models of sustained accretion in the most massive cluster environments. It would suggest that the Phoenix cluster's apparently inefficient feedback mechanism allowed the black hole to grow essentially unchecked for a significant period, gorging on the torrential cooling flow without generating enough energy to shut off its own food supply. This would make Phoenix A a unique laboratory for studying what happens when the feedback loop fails, when the thermostat breaks, and the black hole simply keeps eating. It would also raise questions about how common such objects might be. If Phoenix A's black hole truly reached 100 billion solar masses, are there others like it in equally extreme clusters that we have not yet examined closely enough? Or is this a singular freak, a one-in-a-universe outcome of an exceptionally rare combination of cluster mass, cooling rate, and feedback failure? Now consider what happens if the estimate is too high. Perhaps the true mass is 50 billion solar masses, or 20 billion, or even lower. Such a revision would still leave Phoenix A's black hole among the most massive ever identified, but it would change the story significantly. It would mean that the feedback mechanism, while struggling, was not completely overwhelmed. It would bring the black hole back within a more comfortable range for standard growth models. and it would shift the largest black hole crown to a different candidate, one whose mass estimate might rest on different methods with different strengths and weaknesses. This is not idle speculation. The history of black hole mass estimates at the ultramassive end is littered with revisions. Numbers that were published with confidence have been revised upward or downward as new data became available, or as methods were refined. This is normal science. It is how the field progresses, but it means that any claim about which black hole holds the record must be held lightly, with full awareness that the ranking could change with the next paper. Phoenix A's situation is made even more complex by the nature of its host cluster. The Phoenix cluster is not a calm, well-ordered system. It is violently active, with extreme cooling flows, powerful jets, enormous cavities in the X-ray gas, and a starburst rate that dwarfs anything seen in comparable clusters. Modelling the central black hole's mass in such an environment requires accounting for all of these interacting processes simultaneously. The cooling flow feeds the black hole, but it also forms stars, which changes the stellar density profile, which affects the model's mass estimate. The jets carve cavities, which change the gas distribution, which affects the cooling rate, which feeds back into the accretion rate. Everything is coupled. Everything influences everything else. In a simpler system, where the galaxy is quiescent and the cluster gas is settled, the modelling would be more straightforward. In the Phoenix cluster, the modelling must navigate a web of interconnected extreme processes, any one of which, if modelled incorrectly, could shift the final mass estimate significantly. This is why many astronomers, while acknowledging Phoenix A as an extraordinary object, treat its mass estimate with a degree of caution that they would not apply to, say, the mass of M87 star. The Event Horizon Telescope image of M87 star provided a direct, geometry-based constraint on the black hole's mass. The shadow size, combined with general relativity and the known distance, gave a measurement that was largely independent of modelling assumptions. Phoenix A has no such anchor. Its mass rests on a chain of inference that is impressive in its sophistication, but inherently more fragile than a direct observation. None of this diminishes the importance of the result. Phoenix A is, by any reasonable accounting, one of the most extreme black hole candidates ever identified. Its estimated mass, even if it carries substantial uncertainty, places it in a category occupied by very few objects in the observable universe. The environment it inhabits is genuinely unique. The cooling flow, the starburst, the feedback signatures all point to something happening at the centre of this cluster that is not happening anywhere else we have looked. But the word candidate matters. Phoenix A is a candidate for the title of largest black hole ever found. It is treated as such by the astronomical community, not as a confirmed record holder. The distinction is subtle but important. A confirmed measurement carries the weight of direct observation and independent verification. A candidate carries the weight of careful estimation and physical plausibility. Both are valuable. Both deserve attention. But they are not the same thing, and confusing them leads to the kind of misleading certainty that makes headlines but distorts understanding. Here is what we can say with confidence. The black hole at the centre of the Phoenix cluster is extraordinarily massive. The most widely cited estimates place its mass at approximately 100 billion solar masses, derived from physically motivated modelling of the galaxy and cluster properties. This estimate is consistent with multiple independent lines of evidence, including the extreme cooling flow, the anomalous starburst rate, and the energetic feedback signatures. If accurate, it represents the most massive black hole ever identified and places the object at or near the theoretical ceiling for black hole growth. But the estimate has not been confirmed through direct dynamical measurement. The mass is model dependent. The range of estimates from different approaches spans from tens of billions to 100 billion or more. And the extreme environment of the Phoenix cluster introduces complications that make the modelling more challenging than in more typical systems. This combination of extraordinary scale and irreducible uncertainty is what makes Phoenix are so compelling and so disquieting. It is not a clean record. It is not a simple number you can point to and say, "There, that is the answer, case closed." It is a number that lives at the intersection of cutting-edge observation and theoretical inference, a number that might be right, might be conservatively low, or might be significantly too high. And the tools we would need to resolve the question definitively, the ability to resolve individual stellar orbits or gas motions within the black hole's sphere of influence at a distance of 5.7 billion light-years, do not yet exist. We are left, then, with something profoundly uncomfortable for a species that likes definitive answers. We have found what may be the largest black hole in the observable universe. We have built a strong circumstantial case for its extraordinary mass. We have models that say the number makes physical sense given the environment. And yet we cannot be sure. The uncertainty is not a flaw in the science. It is the science. It is what happens when you try to measure the most extreme objects in the cosmos at distances so vast that the light reaching your telescope left its source when the Earth was barely 1 billion years old. It is what happens when you push the boundaries of observational astronomy to their current limits and find that the limits push back. But if Phoenix A's mass is uncertain, surely there must be a more secure benchmark somewhere in the data. Surely there is a black hole whose mass, while perhaps not as spectacularly large, rests on firmer observational ground. A black hole that scientists can point to with greater confidence and say, "This one we know is enormous, and here is the evidence." It is called TON 618, and for decades it was the name most astronomers reached for when they needed a reliable example of the most massive black holes in the universe. Its story is different from Phoenix A's in almost every way, from the method of discovery to the basis of the mass estimate to the reason it became famous. But its story also carries its own surprises, its own revisions, and its own unsettling lessons about what happens when you try to weigh the most extreme objects in existence. That comparison is where the real tension in this story lives, not in any single number, but in the gap between two different kinds of evidence pointing toward two different kinds of certainty about two different monsters sitting near the top of a leaderboard that was never as stable as it seemed. Long before anyone had heard of Phoenix A, there was a faint blue dot in the northern sky that nobody understood. In 1957, two Mexican astronomers named Braulio Iriarte and Enrique Chavira were conducting a survey of faint blue stars at the Tonantzintla Observatory in central Mexico. The observatory sits in the state of Puebla, surrounded by volcanic highlands, and its Schmidt telescope was being used to photograph patches of sky away from the dense plain of the Milky Way, searching for white dwarfs and other hot blue objects that would stand out against the cooler stellar background. One of the objects they catalogued appeared, in their words, decidedly violet. It was faint, unremarkable in every way except its colour, and they recorded it as entry number 618 in the Tonantzintla catalogue. Nobody paid much attention. The object was just another dot on a photographic plate, one more entry in a list of thousands. It would sit unexamined in the catalogue for over a decade, a cosmic giant hiding in plain sight, mistaken for a nearby star in our own galaxy. The reason nobody recognised what TON 618 truly was is that the concept it represented had not yet been invented. Quasars were not identified as a class of objects until 1963, when astronomer Martin Schmidt recognised that the strange spectral lines of an object called 3C273 could only be explained if the object was extraordinarily distant and therefore extraordinarily luminous. Before that breakthrough, the idea that an object could be billions of light years away and still visible as a point of light on a photographic plate seemed absurd. Nothing could be that bright. Nothing known to physics at the time could produce that much energy from what appeared to be a single point in space. But quasars could. And once the floodgates opened, astronomers began re-examining catalogues of unusual blue objects, looking for others that might share 3C273's bizarre properties. In 1970, Radio emissions were detected coming from the direction of Tonnan Scintilla entry 618. Radio emission from a point source far from the galactic plane was a strong hint. This was not a white dwarf. Shortly afterward, Marie-Helene Ulrich at the McDonald Observatory in Texas obtained optical spectra of the object and confirmed what the radio data suggested. TON 618 was a quasar, and its redshift placed it at a staggering distance. The light reaching Earth from TON 618 had been travelling for approximately 10.8 billion years. The object existed when the universe was only about 3 billion years old, a young cosmos still assembling its first large-scale structures. And despite that almost incomprehensible distance, TON 618 was visible. Not just barely detectable by the most powerful telescopes, but visible as a distinct point source in survey images taken with a modest Schmidt telescope in Mexico. The only way to reconcile that visibility with that distance was to accept that TON 618 was producing energy on a scale that made ordinary galaxies look dim by comparison. The numbers confirmed it. TON 618 has an absolute magnitude of roughly negative 30.7, making it one of the most luminous objects ever detected in the observable universe. Its total power output is estimated at up to roughly 5 times 10 to the 40th watts. To translate that into more human terms, TON 618 shines with the luminosity of approximately 140 trillion suns, not billion, trillion. 140 trillion stellar furnaces, each one capable of sustaining a solar system, and you would need every single one of them burning simultaneously to match the energy output of this single object. Consider what that luminosity means in practical terms. If you could somehow transport TON 618 to the distance of the nearest star, Proxima Centauri, roughly 4 light-years away, it would not merely be the brightest object in the sky, it would turn night into day. Its radiation would sterilize the surface of the Earth. Even at its true distance of 10.8 billion light-years, after the vast majority of its light has been diluted by the expansion of space across most of the observable universe, it remains detectable. It was detectable on photographic plates half a century before astronomers had the conceptual framework to understand what they were seeing. That is the kind of luminosity we are dealing with. Not bright. Not very bright. Bright enough to be seen across most of the observable universe with equipment designed to photograph faint nearby stars. That energy comes from one source. The supermassive black hole at the centre of TON 618 is feeding. Gas, dust, and disrupted stellar material are spiralling inward through an accretion disk, heated to temperatures of millions of degrees by friction and gravitational compression, radiating furiously across the electromagnetic spectrum before crossing the event horizon and vanishing forever. The accretion disk around TON 618 is one of the most energetic environments in the known universe, a maelstrom of superheated plasma orbiting at significant fractions of the speed of light, releasing gravitational potential energy with an efficiency that dwarfs nuclear fusion. While nuclear fusion in stars converts roughly 0.7% of mass into energy, accretion onto a black hole can achieve efficiencies of 5 to 40%, depending on the black hole's spin. At the luminosities exhibited by TON 618, the central engine is converting matter into radiation with an efficiency that ranks among the highest known in nature. The brilliance of TON 618 is both its gift and its curse for astronomers trying to study it. The quasar's glare is so intense that it completely overwhelms the light from its host galaxy. Every galaxy that harbours a quasar is, by definition, a galaxy with an active supermassive black hole at its centre, surrounded by stars, gas, and all the normal components of galactic structure. But in the case of TON 618, the quasar outshines its host so thoroughly that the galaxy itself is invisible. We know it must be there. The black hole did not form in empty space. It grew inside a galaxy, fed by that galaxy's material, shaped by that galaxy's mergers and accretion history. But we cannot see the galaxy directly. We see only the blazing engine at its core, and whatever that engine illuminates in its immediate surroundings. This invisibility of the host galaxy has consequences for mass measurement. One of the most reliable ways to estimate a supermassive black hole's mass in distant active galaxies is a technique called reverberation mapping. The basic idea is elegant. The quasar's central engine varies in brightness over time, flickering as the accretion rate changes. These brightness variations propagate outward at the speed of light, illuminating clouds of gas orbiting at various distances from the black hole. The gas clouds respond to the changing illumination by brightening and fading in turn, but with a time delay that corresponds to the light travel time between the central engine and the clouds. By measuring this time delay and combining it with the velocity of the gas clouds, determined from the width of their spectral emission lines, astronomers can calculate the mass enclosed within the orbit of those clouds. The time delay gives you the distance. The velocity gives you the orbital speed. Together, they give you the mass pulling the gas inward. The method is less direct than tracking individual stellar orbits, as was done for Sagittarius A-star, but it is far more direct than the modelling approach used for Phoenix A. It relies on actual observed velocities of actual observed material orbiting within the black hole's gravitational domain. For TON 618, the key spectral lines used to estimate the black hole's mass come from the broad line region, a zone of fast-moving gas clouds relatively close to the central engine. These clouds orbit the black hole at distances measured in light weeks to light months, close enough to feel its gravitational pull intensely but far enough to remain outside the event horizon. The width of their emission lines tells astronomers how fast the gas is moving. Wider lines mean faster velocities. Faster velocities mean more gravitational pull. More gravitational pull means more mass. The original mass estimate for TON 618's black hole came from work by Ohad Shemer and colleagues, who measured the width of the hydrogen beta emission line for a sample of 29 quasars, including TON 618. The hydrogen beta line is a specific wavelength of light emitted by hydrogen atoms in the broadline region, and its width serves as a proxy for the velocities of the emitting gas. The emission lines in TON 618's spectrum were found to be unusually broad, with the full width at half maximum being the largest of all 29 quasars in the sample, and with hints of gas velocities reaching 10,500 km per second. These were among the highest velocities measured in any quasar in the sample, indicating an exceptionally strong gravitational field. The mass derived from these measurements was approximately 66 billion solar masses. 66 billion. That number made TON 618 one of the most massive black holes ever identified, exceeding the total stellar mass of the Milky Way, which is estimated at roughly 50 to 64 billion solar masses. A single black hole outweighing every star in a major spiral galaxy. The number was extraordinary, and it quickly entered the popular science landscape as the definitive heavyweight champion of black holes. For years, if you search for the largest black hole ever found, TON 618 was the name that came up. Documentaries featured it, infographics compared it to the solar system, science communicators cited it as the ultimate example of gravitational excess. Even the Guinness World Records listed it as the most massive observed black hole, cementing its place in public consciousness as a settled fact. But science does not stand still, and mass estimates, especially at these extremes, are not permanent monuments. In 2019, a study by Gesh and colleagues reanalyzed the spectral data for TON 618 using a different emission line. Instead of hydrogen beta, they used the carbon-4 line, an alternative spectral feature that can provide an independent estimate of gas velocities in the broadline region. The carbon-4 line is emitted by triply ionized carbon atoms, a different species of gas than the hydrogen responsible for the hydrogen beta line. These two types of gas do not necessarily occupy the same region of space around the black hole. They may orbit at different distances, experience different physical conditions, and respond differently to the quasar's radiation field. The carbon-4 line yielded a lower velocity measurement, approximately 2,761 km per second, with an uncertainty of 423 km per second. This lower velocity translated directly into a lower mass estimate of approximately 40.7 billion solar masses. 40.7 billion, still enormous, still among the most massive black holes known, but significantly lower than the original 66 billion. The revision did not dethrone TON 618 from the upper ranks of black hole masses, but it demonstrated something important about the fragility of these measurements. The two estimates, 66 billion and 40.7 billion, were derived from the same observational data, the same quasar, the same telescope observations. The difference came from which spectral line was used to trace the gas velocities and how that line was interpreted. This is not a scandal. It is a well-known challenge in quasar spectroscopy. Different emission lines form at different distances from the central engine under different physical conditions. The hydrogen beta line and the carbon 4 line do not necessarily trace the same population of gas clouds. The carbon 4 line, in particular, is known to be influenced by non-gravitational effects such as radiation pressure and outflows, which can add or subtract velocity in ways that complicate the relationship between line width and black hole mass. The radiation pressure issue deserves closer attention because it cuts to the heart of why measuring ultramassive black holes is so difficult. At the luminosities exhibited by TON 618, the radiation pouring out of the accretion disk is not merely illuminating the surrounding gas clouds, it is pushing them. Photons carry momentum, and when they strike gas clouds or are absorbed by them, they transfer that momentum, accelerating the gas outward. This radiation pressure adds velocity to the gas that has nothing to do with gravity. The gas moves faster than it would under gravitational forces alone. And because the mass estimate depends on interpreting the gas velocity as a measure of gravitational pull, any extra velocity from radiation pressure inflates the apparent mass. Think of it as trying to weigh someone on a scale during an earthquake. The needle would jump around because forces other than the person's weight are acting on the system. Radiation pressure is the earthquake. It shakes the measurement. At moderate quasar luminosities, the effect is small and can be accounted for with standard calibrations. But at the extreme luminosities of TON 618, the radiation pressure may be significant enough to bias the mass estimate substantially. Some researchers have argued that radiation pressure corrections should be applied to the mass estimates of the most luminous quasars, which would generally push the numbers downward. Others counter that the standard calibrations already incorporate luminosity effects to some degree, and that additional corrections risk overcorrecting and underestimating the true mass. The debate is ongoing, technical, and unlikely to be resolved without significantly improved data on the structure and dynamics of the broadline region in extreme quasars. But the consequence for our story is clear. The mass of TON 618's black hole is not a single number. It is a range, spanning from roughly 40 billion to 66 billion solar masses, with different analyses favouring different points within that range, and with the true value depending on physical effects that are difficult to disentangle at cosmological distances. Now, to feel what that range means physically, consider what TON 618 looks like at both ends of its mass estimate. At 40.7 billion solar masses, the revised lower estimate, the event horizon already spans roughly 800 astronomical units in radius. That is more than 20 times the distance from the Sun to Pluto. Light needs approximately 1 month to circle its circumference. If you place this black hole at the centre of our solar system, its event horizon would extend roughly 20 times farther than the orbit of Pluto in every direction. Everything you have ever known about our planetary neighbourhood, every world we have ever studied, every probe we have ever launched, would fit inside this event horizon with room to spare. Vast, empty, incomprehensible room. At 66 billion solar masses, the original higher estimate, the event horizon grows to roughly 1,300 astronomical units in radius, more than 30 times the distance from the Sun to Pluto. Light now needs nearly 7 weeks to complete a full circuit. The event horizon at this mass is larger than the entire region of space that our most distant spacecraft has traversed in nearly 50 years of travel. Multiplied by a factor of 8, It is a sphere of no return, so enormous that stellar systems could orbit within it, oblivious to their fate. For years before the inward curvature of space revealed that escape had become impossible, the difference between these two scales is itself enormous. The event horizon at 66 billion solar masses is roughly 60% larger than the event horizon at 40.7 billion. That gap, the physical difference between the two competing mass estimates, represents a volume of space larger than anything in our solar system. And this gap exists not because the measurements disagree about what TON 618 is, but because they disagree about which spectral line best captures the gravitational motion of gas orbiting billions of light years away. Now, compare this situation with Phoenix A. TON 618's mass estimate, for all its uncertainty, is based on direct spectroscopic observation of material orbiting within the black hole's gravitational sphere of influence. The gas is real. The velocities are measured. The relationship between velocity and mass is grounded in well-tested physics. The uncertainties arise from interpreting which spectral line best represents the gravitational motion, from calibrating the technique at extreme luminosities, and from accounting for non-gravitational effects like radiation pressure. These are significant uncertainties, but they are uncertainties within a fundamentally observational framework. Phoenix A's mass estimate, by contrast, is based on modelling the growth history of the black hole using the observable properties of its host galaxy and cluster environment. The observations that feed the model are real: the stellar density profile, the cooling rate, the X-ray luminosity, the jet feedback signatures. But the mass itself is inferred rather than measured. It is the output of a theoretical framework rather than a direct reading from a gravitational speedometer. The distinction is not between good science and bad science. Both approaches are rigorous and well motivated. The distinction is between different kinds of evidence, carrying different kinds of confidence, pointing toward different kinds of conclusions. This is where the comparison between Phoenix A and TON 618 becomes genuinely illuminating and genuinely uncomfortable. Phoenix A's estimated mass at 100 billion solar masses is higher than any estimate for TON 618. If you take the numbers at face value, Phoenix A wins. But taking numbers at face value is exactly what this story warns against. Phoenix A's estimate is model-derived and has not been independently confirmed through spectroscopic or dynamical methods. Its range of estimates from different approaches spans from tens of billions to 100 billion or more. TON 618's estimate is spectroscopically based, but spans a range from roughly 40 to 66 billion solar masses, depending on the method. The gap between them could be as large as 60 billion solar masses, or as small as 34 billion. All the estimates could overlap entirely if Phoenix A's true mass turns out to be at the lower end of its range, and TON 618's turns out to be at the higher end. The leaderboard, in other words, is not a leaderboard. It is a cloud of overlapping probability distributions, each one centered on a best estimate, but spreading outward across tens of billions of solar masses of uncertainty. Asking which black hole is definitively the largest is like asking which cloud in the sky is definitively the tallest. The question assumes a precision that the data cannot support, and yet this very ambiguity is what makes TON 618 such an important object in the story of ultramassive black holes. Because even at the lower end of its mass range, around 40 billion solar masses, TON 618 is a genuinely extraordinary object. Its event horizon at that mass is already vastly larger than our entire planetary system. It outweighs billions of stars, and its existence is supported by direct spectroscopic evidence, not modelling. This makes TON 618 what scientists sometimes informally call a clean benchmark. Not clean in the sense that all uncertainties are resolved, but clean in the sense that the evidence is observational rather than model-dependent, and the object has been studied for decades by multiple independent groups using multiple independent methods. The mass may not be known precisely, but the range is constrained by real measurements of real gas moving at real velocities. When astronomers need a reliable example of an ultramassive black hole to anchor discussions, comparisons, or theoretical arguments, TO618 is the name they reach for. Phoenix A, by contrast, is the frontier. It may be larger, it may be the true champion, but its mass is less securely pinned down, and its status depends more heavily on the correctness of specific theoretical models. In the informal taxonomy of extreme black holes, TON 618 is the established heavyweight, and Phoenix A is the challenger whose weigh-in is still being disputed. TON 618's Lyman Alpha Nebula provides one more piece of this evolving puzzle, and it reveals something about the sheer physical strangeness of the environment these ultramassive objects create around themselves. In 2021, observations by the Atacama Large Millimeter Array revealed that TON 618 is surrounded by an enormous cloud of gas classified as a Lyman Alpha blob, a vast nebula of neutral hydrogen glowing in ultraviolet light under the quasar's intense radiation. This nebula spans at least 100 kiloparsecs in diameter, roughly 330,000 light-years, making it more than twice the diameter of the Milky Way. Pause on that for a moment. The gas structure surrounding TON 618, not the black hole itself, not the accretion disk, not the host galaxy, but just the illuminated cloud of hydrogen enveloping the system, is larger than our entire galaxy. If you could see this nebula from a neighbouring galaxy cluster, it would dwarf the Milky Way the way a cathedral dwarfs a birdhouse. And this structure is not a static relic. It is actively shaped by the black hole's output. Within the nebula lie two components: an inner molecular outflow driven by the black hole's jets, and an extended cold molecular gas reservoir in its circumgalactic medium, each containing approximately 50 billion solar masses of material. Both components are aligned with the powerful radio jets produced by the central black hole. This alignment is not coincidental. It reveals that the black hole has been sculpting its environment on scales of hundreds of thousands of light-years, for timescales measured in hundreds of millions of years at minimum. The jets have been driving material outward, shaping the gas distribution, regulating the flow of fuel that might otherwise fall inward and feed further growth. TON 618's nebula is a fossil record of the black hole's activity written across a canvas twice the size of the Milky Way, a map of energy and matter shaped by a single gravitational engine over cosmic time. This environmental complexity is relevant to the mass question because it illustrates how much is happening around these objects that we are only beginning to understand. The mass of the central black hole is one number in a vastly complicated system. The gas reservoir, the jet activity, the host galaxy, the surrounding intergalactic medium, all of these components interact and influence each other in ways that affect our ability to measure any single property with precision. This distinction between methods matters far beyond the question of which object holds the record. It reveals something deep about how science works at the boundary of the known, in the comfortable middle ranges of black hole masses, where objects weigh a few million to a few billion solar masses. The measurement methods are mature, the cross-checks are numerous, and the community can reach consensus relatively easily. Everyone agrees that Sagittarius A-star weighs about 4 million solar masses. Everyone agrees that M87 star weighs roughly 6 to 7 billion. The error bars are small enough that the rankings are stable, but at the ultramassive end, above 10 billion solar masses, the error bars expand, the methods diverge, and consensus becomes harder to achieve. The same object can be assigned different masses by different teams using different methods, and both teams can be doing excellent science. The disagreement is not a sign of sloppiness. It is a sign that the measurements are pushing up against fundamental limits of observational precision at cosmological distances. When you plot all of the ultramassive estimates on a single chart, you get something that looks like a ranking. But the apparent ranking is an artifact of presenting central estimates without fully displaying the uncertainty. If you included the full error bars for every object, many of the bars would overlap, Objects that appear to be clearly separated in mass might actually be statistically consistent with each other. The largest black hole might be any one of several candidates, depending on which estimates you trust and how you handle the uncertainties. This is not a comfortable situation for a field that would like to make definitive statements about the most extreme objects in the universe. It is not a comfortable situation for science communicators who want to present clear, simple facts to the public. And it is definitely not a comfortable situation for viewers who clicked on a video expecting to learn which black hole is the biggest and receive a straight answer. But it is the truth. And the truth, in this case, is more interesting than the simple answer would have been. Because the instability of the rankings is not just a measurement problem, it is a clue about the nature of these objects themselves. Black holes at the ultramassive end of the scale live in extreme environments that are inherently difficult to characterize. They are far away. They are embedded in complex systems where multiple physical processes interact. They produce prodigious amounts of radiation that can overwhelm the signatures scientists need to measure. Their masses push against theoretical limits, raising questions about whether our models of black hole growth are complete. Every one of these challenges contributes to the uncertainty. And every one of these challenges is, in itself, a scientific frontier. The difficulty of measuring ultramassive black holes is not an obstacle to be overcome and then forgotten. It is a permanent feature of the landscape, a consequence of trying to measure the most extreme objects at the greatest distances using the most indirect methods available. And here is the unsettling realization that connects TON 6-18 back to Phoenix A and forward to the deeper question this story is building toward. Both of these objects, the established benchmark and the extreme challenger, carry substantial uncertainties in their mass estimates. Both have been revised or could be revised as new data becomes available. Both exist in environments so extreme that characterizing them fully is beyond current observational capabilities. And both sit in a mass range where the difference between 40 billion and 100 billion solar masses, which sounds like a vast gap, might actually be narrower than it appears once the full uncertainties are accounted for. The question of which black hole is truly the largest is not a question with a clean answer. It is a question that exposes the limits of what we can currently know about the most extreme objects in the cosmos. And the limits are not temporary inconveniences that will be resolved next year with a better telescope. Some of them are fundamental, rooted in the distances involved, the indirectness of the methods, and the complexity of the environments. This does not mean the quest is futile. Every new observation narrows the uncertainties. Every improved technique sharpens the estimates. The field is making real progress, and future instruments like the extremely large telescope, the 30-meter telescope, and next-generation space-based observatories will push the boundaries of what we can resolve at cosmological distances. But the progress is asymptotic. We will get closer to the truth without ever reaching a point where ultramassive black hole masses are known with the same confidence as Sagittarius A-stars. The rankings will remain written in pencil. The leaderboard will continue to shift. And the honest answer to the question of which black hole is the largest will continue to be. It depends on what you mean by no. TON 6-18 showed us that even the safest benchmark carries revision. Phoenix A showed us that the most extreme candidate carries uncertainty. Together, they reveal something that this story must now confront directly. The real terror is not which black hole holds the record. The real terror is what these objects tell us about a universe that produces gravitational monsters so extreme that even our best tools for measuring them begin to buckle under the weight. Something stranger and more disturbing than a simple record is waiting at the end of this story. It is not a bigger number. It is the realization that, at the ultramassive frontier, the numbers themselves stop behaving the way we expect them to, and the question of which black hole is the largest may not have a stable answer at all. There is a moment in every encounter with extreme scale when the human mind quietly gives up, not dramatically. Not with panic or confusion, it simply stops converting numbers into meaning. You hear 100 billion solar masses, and the words pass through you like background noise. You nod. You think you understand. But the feeling that accompanied earlier numbers, the gut-level sense of enormity you felt when contemplating Sagittarius A-star at 4 million solar masses or M87 star at 6.5 billion, has gone silent. The emotional register has flatlined, not because you have become braver or more sophisticated, because the number has outrun your brain's ability to attach weight to it. This is not a failure of intelligence. It is a feature of how human cognition evolved. Our ancestors needed to distinguish between 3 predators and 30. They needed to estimate whether a food source would last 1 week or 5. They did not need to distinguish between 40 billion and 100 billion of anything. There was never a survival advantage in feeling the difference between those numbers in your gut. So the machinery was never built. And now, standing at the threshold of the most extreme objects in the observable universe, we find ourselves carrying a calculator that only works up to a certain size, staring at a blackboard covered in figures that exceed its range. This cognitive collapse is not a side note to the story of ultramassive black holes. It is central to it, because the difficulty humans face in feeling the difference between 40 billion and 100 billion solar masses mirrors, in a strange and uncomfortable way, the difficulty that science itself faces in measuring that difference. The numbers are so large, the objects so distant, the methods so indirect, that the gap between competing estimates can span tens of billions of solar masses without anyone being able to definitively say where the truth lies. The human mind goes numb at these scales, and the scientific instruments, for all their extraordinary precision, begin to blur. This convergence between cognitive limitation and observational limitation is what makes the ultramassive regime so uniquely unsettling. It is not just that these black holes are big, it is that they are big enough to break both our intuition and our measurement tools at the same time. Consider what it would take to resolve the question of whether Phoenix A or Ton 618 is truly more massive. You would need to directly observe the motion of matter, stars or gas, within the gravitational sphere of influence of each black hole. For Phoenix A, that sphere of influence, the region where the black hole's gravity dominates over the galaxy's stellar mass, subtends an angle on the sky so small that no current or near-future telescope can resolve it from a distance of 5.7 billion light-years. For Ton 618, the situation is even worse. The quasar's blinding glare washes out any hope of resolving the host galaxy's central dynamics, and the object is 10.8 billion light-years away. Even the next generation of extremely large ground-based telescopes, with mirrors 30 to 40 meters across, will struggle to achieve the angular resolution needed to probe these regions directly. This means that for the foreseeable future, the masses of the most extreme black hole candidates will continue to depend on indirect methods, reverberation mapping for active quasars like Ton 618, modeling for objects like Phoenix A embedded in complex cluster environments, scaling relations calibrated on less extreme systems for others. Each method will continue to improve incrementally as new data accumulates and analysis techniques are refined. But the fundamental challenge remains. You are trying to weigh the heaviest objects in the universe from the greatest possible distances, using proxies rather than direct measurement. The uncertainties will shrink, but they will not vanish. And this is where the story pivots from being about 2 specific black holes to being about something larger and more disturbing. Because the instability at the top of the mass rankings is not an accident. It is not a temporary state of affairs that will be cleaned up once the next generation of telescopes comes online. It is a structural feature of how the universe distributes mass at the most extreme scales, and how our methods of measurement interact with that distribution. Think of it this way. In the range of supermassive black holes from 1 million to a few billion solar masses, the population is large enough and the measurements are precise enough that the rankings are relatively stable. There are hundreds of well-measured black holes in this range. Their masses cluster in predictable ways around the scaling relations. The error bars are small compared to the gaps between entries. The leaderboard makes sense. But at the ultramassive end, above 10 billion solar masses, the population thins dramatically. There are perhaps a few dozen candidates in this range across the entire observable universe. Each one lives in an unusual environment. Each one is measured by a different combination of methods. Each measurement carries uncertainties that span billions of solar masses, and the objects themselves are separated by mass gaps that may be smaller than the error bars on individual measurements. In this regime, ranking becomes statistically meaningless. Saying that Phoenix A at 100 billion solar masses is larger than Ton 618 at 40 to 66 billion solar masses sounds definitive. But when you include the full uncertainty on both measurements, the probability distributions overlap enough that the question of which is truly more massive has no confident answer. You could flip the ranking without violating any observational constraint. Both orderings are consistent with the data. This is not a niche technical point. It strikes at the heart of what viewers expect when they encounter a title like "The Largest Black Hole Ever Found." They expect a winner, a single object that sits unambiguously at the top, a definitive answer to a straightforward question. What they find instead is a statistical fog where several candidates jostle for position within overlapping clouds of uncertainty, and the very concept of a clear champion dissolves under scrutiny. The physicist and black hole researcher Priyamvada Natarajan, based at the Department of Astronomy at Yale University, has spent years studying the upper mass limit of supermassive black holes. Her work, along with that of her colleagues, has approached the question not by trying to determine which specific black hole is the largest, but by asking a more fundamental question. Is there a maximum mass that any black hole can achieve? The answer, according to Natarajan and her collaborators, appears to be yes. Their research suggests that a natural ceiling exists at approximately 100 billion solar masses. This limit arises not from any single physical process, but from the convergence of several. Black holes grow through accretion and mergers. Accretion is limited by the Eddington luminosity, the point at which radiation pressure from the infalling material balances gravitational attraction, creating a natural throttle on how fast material can be consumed. Mergers add mass in discrete jumps but require the black hole's host galaxy to collide and merge with another massive galaxy, events that become less frequent as the universe ages and expansion carries potential merger partners apart. Beyond these growth mechanisms, there is the feedback problem. As a black hole grows, its energy output increases. The jets, winds, and radiation it produces heat the surrounding gas, making it harder for new material to cool, condense, and fall inward. This self-regulating feedback loop acts as a governor on growth. The bigger the black hole gets, the harder it becomes to feed it further. At some point, the feedback becomes so effective that the black hole essentially starves itself, unable to attract new fuel faster than its own energy output disperses it. Natarajan's models incorporate all of these effects and predict that the maximum achievable mass converges on roughly 100 billion solar masses, depending on the specific assumptions about seed mass, growth history, and feedback efficiency. This number is not a hard wall enforced by a single law of physics. It is a soft ceiling imposed by the combined weight of multiple independent constraints. A black hole could in principle exceed it under unusual circumstances, such as an extraordinarily efficient period of super Eddington accretion or a rapid sequence of major mergers. But such circumstances would be rare, and significantly exceeding the ceiling would require conditions that are difficult to arrange within the standard framework of galaxy and black hole co-evolution. If this theoretical ceiling is correct, then Phoenix A, with its estimated mass of 100 billion solar masses, sits right at the limit. It is not just the most massive black hole candidate we have identified. It may be pressing against the wall of what the universe can produce. This is either a remarkable coincidence, a confirmation of the theoretical models, or a sign that the mass estimate is inflated by the modeling assumptions and the true mass is lower. Each interpretation leads in a different direction. If Phoenix A truly reaches the ceiling, It validates decades of theoretical work on black hole growth and feedback. It means we have found an object that grew as large as physics allows, stopped, and now sits at the summit of a growth curve that no black hole in the observable universe is likely to exceed. That is a profound and satisfying conclusion. It would mean the universe has a speed limit for gravitational collapse, and we have found an object parked right at the boundary. But if the true mass is significantly lower, say 50 or 60 billion solar masses, then the ceiling has not been reached, and the question of whether any black hole can reach it remains open. Future observations might find a more convincing candidate, or theoretical refinements might lower the predicted ceiling, or the whole concept of a maximum mass might turn out to be more nuanced than current models suggest. And there is a third possibility, the most unsettling one. What if the ceiling is real, but our measurements are too imprecise to determine whether any specific object has actually reached it? What if we are condemned, by the distances involved and the indirectness of our methods, to a permanent state of uncertainty about whether the most extreme candidates genuinely sit at the maximum or merely appear to? This third possibility is the one that haunts the ultramassive frontier. It suggests that there is a category of scientific questions that are answerable in principle, but not in practice, given the limitations of what we can observe from our position in the cosmos. The universe may produce black holes at the theoretical maximum. We may even have detected one. But confirming it with the level of certainty that science demands may be beyond our reach for generations, if not permanently. The discomfort this creates is not just scientific, it is philosophical. We are accustomed to thinking of science as a process that converges on truth. Given enough time, enough data, enough ingenuity, the right answer will eventually emerge. But the ultramassive black hole problem suggests that convergence has limits. Some truths may remain permanently blurred, not because the universe is hiding them, but because the evidence we need to resolve them is diluted beyond recovery by distance, glare, and complexity. This is the deeper terror that Phoenix A and Ton 6/18, considered together, reveal. The terror is not that these objects are big. Bigness, by itself, is just a number. The terror is that they are big enough to expose the fragility of our confidence, big enough to make the question of which one is largest genuinely unanswerable with current tools, big enough to sit at a boundary where physics, observation, and human cognition all begin to strain simultaneously. And there is still one more layer to the unease, one that has been building quietly throughout this entire story. It is the realization that even if we could measure every ultramassive black hole with perfect precision, even if we could rank them unambiguously from largest to smallest, the resulting list would be deeply strange. Not strange because the numbers are large. Strange because the numbers stop feeling like properties of distinct objects and start feeling like arbitrary coordinates in a continuum of excess. At moderate masses, black holes feel like things. Sagittarius A-star is a specific object with specific properties. You can talk about its mass, its spin, its effect on nearby stars, and all of these properties feel like they belong to a discrete entity. It has an identity. It is our black hole, the one at the center of our galaxy, and it is different from the one at the center of Andromeda or the one at the center of M87. But at the ultramassive end, individuality begins to dissolve. A black hole of 40 billion solar masses and a black hole of 100 billion solar masses differ in mass by a factor of 2.5. In any other context, a factor of 2.5 would feel significant. A cat and a dog differ in mass by a similar factor and nobody confuses them. But at the ultramassive scale, the factor of 2.5 does not correspond to any qualitative difference in the nature of the object. Both are featureless spheres of event horizon. Both are characterized entirely by mass, spin, and charge. Both have been stripped of all internal structure by the same equations of general relativity. The only thing that distinguishes them is a number. And the number has grown so large that the human mind cannot feel the difference. This is the regime where black holes stop feeling like astrophysical objects and start feeling like abstract extremes. They are no longer things you can visualize or compare to familiar reference. The event horizon of a 40 billion solar mass black hole is already larger than any structure in our solar system. Making it 2.5 times bigger does not change the picture in any way your brain can render. It is already beyond visualization. Scaling it up further just moves you deeper into a region of mathematical abstraction where the numbers keep climbing but the mental image stays frozen. And yet the numbers do matter, because they encode real physical differences. A black hole of 100 billion solar masses has an event horizon roughly 2.5 times larger than one of 40 billion solar masses. It processes infalling material differently. Its tidal forces at the event horizon are weaker, paradoxically, because larger black holes have gentler gradients at their horizons. An astronaut falling into a 100 billion solar mass black hole would cross the event horizon without feeling any tidal stretching at all. The deadly forces would come later, much later, as the astronaut plunged deeper toward the singularity. The larger the black hole, the more gentle the threshold, and the more delayed the destruction. This inversion of intuition, bigger means gentler at the boundary, is one of the many ways that ultramassive black holes defy the expectations people bring to them. The popular image of a black hole as a violent, crushing maw that destroys everything at its edge is accurate for stellar mass black holes and even for moderately supermassive ones. But at the ultramassive end, the event horizon becomes almost serene. You would not know you had crossed it. The violence is still there, but it is hidden deeper inside, postponed, waiting. There is something genuinely eerie about an object so large that its most dangerous boundary is imperceptible to a human falling through it. It suggests a kind of cosmic stealth, a predator so vast that its victims do not realize they have been captured until long after the point of no return. The event horizon of a 100 billion solar mass black hole is not a wall or a surface. It is a region of space that looks and feels like ordinary space from the inside, indistinguishable from the void around it, except that every trajectory within it curves inexorably inward. There is no escape, but there is also no warning, no signpost, no sensation of crossing a threshold. Just the quiet, irreversible realization, if you had instruments sensitive enough to detect it, that the universe outside has become forever unreachable. This quality of imperceptible enormity is perhaps the most fitting metaphor for what the ultramassive frontier represents in the broader story of human knowledge. We have discovered objects so extreme that even the act of identifying which one is the most extreme becomes uncertain. We have pushed our measurements to distances so great that the evidence blurs and the rankings dissolve into overlapping clouds of probability. We have encountered a theoretical ceiling that tells us these objects should not exceed a certain mass, but we cannot confirm whether any specific object has reached it, and through all of this, the universe gives no indication that it considers any of this remarkable. The Phoenix cluster does not know it is extreme. TON 618 does not know it is luminous. The black holes at their centers do not know they are large. They simply exist, products of gravity and time, and the initial conditions of a cosmos that set matter in motion 13.8 billion years ago and has been letting it fall inward ever since. The real terror, the one this story has been building toward from the beginning, is not that Phoenix A may be the largest black hole ever found. That is a claim about a number, and numbers can be revised. The real terror is what these objects collectively reveal about the universe we inhabit. They reveal that the cosmos produces gravitational engines of such staggering scale that our best instruments can barely distinguish between them. They reveal that the familiar language of records and rankings, which works perfectly well for mountains and oceans, and even ordinary galaxies, begins to fail when applied to objects measured in tens of billions of solar masses at distances measured in billions of light years. They reveal that the boundary between confirmed observation and careful estimation becomes thin and porous at exactly the point where the stakes are highest, where the most extreme claims require the most extraordinary evidence, and they reveal something else, something quieter and more lasting than any single mass estimate. They reveal that the universe does not care about our categories. It does not organize its black holes into neat rankings for our convenience. It does not pause at the boundary of what we can comfortably measure and say, "Here, let me make this one a bit clearer for you." It produces what it produces, in whatever quantities gravity and time allow, and leaves us to sort out the details with whatever tools we can build. Phoenix A may be the largest black hole humanity has ever identified, or it may be one of several candidates clustered near a theoretical ceiling, indistinguishable in mass within the precision of current methods. TON 618 may be the safer benchmark, or it may be a significantly less massive object whose original estimate was inflated by the choice of spectral line. The true ranking may not be knowable with current technology, and the theoretical ceiling itself may be approximate, a soft boundary rather than a hard wall, permeable under conditions we have not yet imagined. What remains, after all the uncertainty is acknowledged and all the caveats are stated, is the scale itself. Not the scale of any one object, but the scale of the regime. A regime where black holes weigh tens of billions of suns, where event horizons span thousands of astronomical units, where the gravitational influence of a single object rivals the stellar mass of an entire galaxy, where the most extreme candidates press against theoretical limits that we are not sure we have correctly calculated, where the question of which one is the biggest is less important than the fact that any of them exist at all. That existence is what should keep you awake, not because these objects threaten Earth. They do not. Phoenix A is 5.7 billion light-years away. TON 618 is nearly twice that distance. They are cosmologically remote, utterly irrelevant to the daily mechanics of life on our small planet, orbiting our modest star in our unremarkable spiral arm. But their existence tells us something about the universe's capacity for excess. It tells us that gravity, given enough matter and enough time and the right conditions, will build structures so extreme that they strain the vocabulary of the scientists who study them. Supermassive was not enough. We needed ultramassive. And even ultramassive may not be enough if future observations reveal objects that force us to invent yet another prefix. The universe builds things that are too large to rank, too distant to measure cleanly, and too extreme to fit comfortably into the categories we construct to make sense of reality. Phoenix A and TON 618 are not just entries on a list. They are signals from a cosmos that operates at scales where human confidence becomes thin, where observational certainty becomes fragile, and where even the most basic question, which one is the biggest, turns out to have no stable answer. That instability is not a failure, it is a revelation. It tells us that the frontier of knowledge is not a clean line that advances uniformly forward. It is a ragged edge, thicker in some places and thinner in others, where what we know shades gradually into what we estimate, and what we estimate shades into what we suspect, and what we suspect eventually dissolves into the vast dark of what we do not and perhaps cannot know. The largest black hole we have ever found may be Phoenix A, or it may be something we have not yet detected, lurking in a galaxy cluster we have not yet surveyed, in a corner of the sky we have not yet pointed our telescopes toward. The universe is large. Our surveys are incomplete. The most extreme objects tend to be rare, and rare objects tend to be found last. But wherever the true champion sits, and whatever its mass turns out to be when our instruments finally become sharp enough to measure it with the confidence it deserves, one thing is already clear. The universe produces black holes so massive that the act of crowning a winner becomes an exercise in navigating uncertainty. And that uncertainty, far from being a limitation to overcome, is itself the message. The cosmos is telling us, in the only language it knows, the language of gravity and light and distance and time, that its most extreme creations exist at the edge of what we can confidently describe, not beyond that edge, not safely on this side of it, right at the boundary, where knowledge and ignorance meet, where measurement and estimation blur, and where the largest black holes sit like monuments to the universe's capacity to exceed our ability to comprehend it. That is the terrifying size of the largest black hole we have ever found. Not a number, not a name, a boundary. The place where human understanding reaches its current limit and the universe, indifferent and immense, keeps going.